Okay, hello everyone, this is Puya. So I was told that some of the practice questions I gave you is not very clear, so I want to solve a few of them. First of all, I want to tell you how to derive a transfer function. So let's just come up with let's just go with one of the examples we have in the practice questions. So we had something like this. V in here, an op amp here, and then let's just go with something like this. A parallel resistor with a capacitor. So let's call this one R1 and C1, and this one R2 and C2. Okay, and what we want to find is the ratio between VO and VI, right? So the key to that is basically just apply the very basic rules that we know about electric circuits. Ohm's law, Kirchhoff's current law, KCL, and Kirchhoff's voltage law, KVL. Right? And the other thing that we have to know is the impedance for capacitor, which I'm sure that you guys already are familiar with it, 1 over j omega c. Okay, and you can see in this circuit we have a negative feedback, right? And if you remember from the op amp section, when you have negative feedback, the op amp is capable of maintaining these two non-inverting and inverting pins to have equal voltages. And since this non-inverting pin is grounded, this is actually going to be a virtual ground. Okay, so that basically means that its potential, it's going to be zero. Its voltage, it's going to be zero. Okay, if that's the case, then it's very easy to find this current. Right, that current, it's going to be V in over R1 plus 1 over j omega C1, right, which is the impedance of this series resistor with this capacitor. And this current, it's going to be the current that goes through R2 plus the current that goes through C2, right? What's the current that goes through R2? It's going to be 0 minus VO, that's the voltage across R2, so it's going to be negative VO divided by R2 plus negative VO divided by the impedance of this one, which is 1 over j omega C2. Okay, let me actually write this here now. If I simplify this, we have V in times j omega C1 divided by R1, divided by R plus j omega R1 C1 is equal to, right, this part, I multiplied the numerator and denominator by j omega C1, so that's what we have. And on this part we have VO, I'll just factor out VO, maybe just do negative VO. And we have 1 over R2 plus, if you just inverse this, it would be j omega C2. Okay, and if I simplify this, it's going to be negative VO times 1 plus j omega R2 C2 divided by R2. We're almost done, right? We found the relationship between VO and VI. Now, let me just divide the two sides by V in, so then we have VO divided by V in is equal to, then I'll take this one to the other side, it would be negative R2 over 1 plus j omega r2c2 times j omega c1 divided by 1 plus j omega r1c1. Okay, so for the rest of the circuits that you have in question 1, you just basically have to follow the same steps. It's just either KCL or KVL, and as long as you know that the impedance of a capacitor is 1 over j omega c, and for an inductor is j omega l, then you're going to be fine. Okay. Now, the other thing that I realized that it was challenging for you was doing the Bode plot. So I want to explain Bode plot from scratch. Okay, so first of all, let's assume that we have a fraction. Let's say like we have a function f of x is equal to x minus 4 times x plus 5 times x minus 3 times x plus root 2. Okay, so we have this concept in control theory and in math, poles and zeros. Okay, so for a function, poles are the values of the variable that make the denominator equal to 0. So for this function, there are two poles, 4 and negative 5. And zeros are the values of the variable that make the numerator equal to 0. So for this one, excuse me, it's x equal to 3 and x equal to negative root 2. Okay, so keep this in mind. Now we're gonna go back to transfer function. So I'm just gonna come up with something that would be very general. So 1 plus j omega times 100 plus j omega times 20 times let's like, okay, I'm just gonna make this very difficult, but that's okay. 10 plus j omega. Not very difficult, but I wanted to start with something easy, but that's okay. I'm just gonna do it step by step. Okay, so so first of all, look at this one. How do we find the poles and zeros here? So in the frequency plane, or in the also like it's also called S plane, we know that the real part belongs to the attenuation or doesn't have any frequency value, and we know that the frequencies are gonna have imaginary components. So I want to find at what frequencies these ones are gonna be